We are now ready to start talking about some limit laws and some techniques for calculating limits beyond using tables and graphs. And so we're going to build up a whole bank of limit laws in this section, and then we're going to utilize those to actually calculate and find limits. So let's start by just a quick recall on where we are at so far. So right now, we've introduced the notation. We've talked about for a function to have a limit, the limit of a function as x approaches a is equal to some value L. What does that mean? That means that as x approaches a, now I will say this, as x approaches a, there's no direction given here. Notice here, this is just as x approaches a, it's a non-directional statement that I've made here. So that means as x approaches a, and maybe in parentheses, we would want to make a note here from both directions. Unless it's a directional limit. So a directional limit we've spent some time talking about, but that is if we were approaching a from the left or approaching a from the right. Okay, so this notation, when there is no direction given, means from both directions. So as x approaches a, the function f of x approaches L, this value L. So that's what we're talking about when we talk about a limit. So if we have a graph and we're talking about a graphical approach and we've spent some time, we don't even care, right here, let's just call that A and even say that the function has a hole right there. Okay. So even if we have this function right here, we would still, and this value here would be our L in this case. So this would be saying that this would be a graphical description of what we've just drawn right here. The limit of a function as x approaches a is equal to L means that from both directions, as the x values approach a, so when it's non-directional coming from both ways, we look from both ways, the function itself is approaching this value L, and that's exactly what this graph does. Okay, so that's a quick review of where we're at in our notation, and now we're going to jump into what if we didn't have a graph, or we didn't want to make a graph, or we didn't want to make a table, we didn't want to have to do this with a lot of computation. What if we wanted to apply some laws? So what are the limit laws that we can apply? And I'm going to have a couple of tables here of limit laws, and we're going to go through them one by one and then spend more of our time in the examples using them. So please freeze the screen and take some notes on these. These are the limit laws. These are the ones that we're going to be able to use. And we're going to say if we, I'm going to zoom in a little bit and get them up there on the screen. There we go. We're going to say this. If we have two functions, we'll call them f of x and g of x, such that they both have limits as x approaches a. So the limit of f of x as x approaches a is equal to L, and the limit of g of x as x approaches a is equal to R. So we've got these two functions, and they each have limits. Then what the limit laws say, and to me, as we utilize these limit laws, I hope they become a little just more intuitive to you. They do work, limit laws work in a way I think that is intuitive to how functions work. So let's go through these laws. So we have the sum or the difference law, and the sum or the difference law says that if we take the limit of the sum or difference of two functions, then we can look at the sum or the difference of each individual limit. So essentially running the limit through that sum or difference and looking at each of those functions individually, and then adding or subtracting those two results. The constant multiple law says that we can pull out a constant, then take the limit. The product law says that if we have a product of two functions whose limits exist, then that is the same as taking the product of the two individual limits. The quotient law says essentially the same thing, but in terms of a quotient, that if we have a quotient of two functions, we can take the limit of that quotient, then we could take the limit of the numerator over the limit of the denominator. That is true as long as, we do of course have this restriction that g of x is not equal to 0. And the power law says that we can actually run the limit inside of a power or an exponent on a function, and we can take the limit of the function and then raise it to the power. Okay, so those are our first set of limit laws, and then we have another set of limit laws that are right here. And this says that if we have a constant, and again have these same two functions, f of x and g of x, whose limits exist as x approaches a, and if we have, this actually doesn't involve f of x at all, this is just talking about x and c for these first couple. The constant limit law says that if you have a constant, that the limit of a constant is itself that constant. Of course, that a constant function remains constant across its entire domain. The linear limit law, and I kind of gave that one its name here, that if we take the limit of x as x approaches a, that's going to be a. And the nth power limit law says that if we have x to the nth, this is putting actually this linear limit law number 7 together with the power law from the previous table, that if we have a power, that's going to be just x to the a. The nth root law, again, have to be a little bit careful with roots because of even roots. You have to assume that you have a positive argument for an even root. So there is some notation here, some restrictions, I guess, on this law. If n is even, we will just make the assumption that a is greater than 0. If n were odd, an odd root, it doesn't matter. So the limit of the nth root of x is actually just the nth root of a as x approaches a. And we can even apply this if we have an actual function, and the function is greater than 0, if n is even, again, being careful with our roots and even roots, domain of even roots. But if we take the limit of the nth root of f of x, that's the same as taking the nth root of the limit of the function, which we said above was equal to L. So that would be the nth root of L. So these are a lot of laws, and it's good to write these all down and know that we can use them. But I want to spend more time in this video actually looking at some examples than going through each of these individual, writing out each of these individuals. So I just typed them up for us, and so utilize them, and we will move into the examples. So let's start with a graphical example. So suppose we had two graphs of f of x and g of x, and we wanted to find some limits. So what if we started by looking at the limit of f of x minus 7 times g of x as x approaches 1? So first of all, just step by step, to begin with, we'll write these out step by step so we can see these limit laws in action. But step by step, what our limit laws say is that we could actually look at this as the limit of f of x as x approaches 1 minus, using the sum and the difference, the limit, sum and the difference law, as x approaches 1 of 7 times g of x. So that's saying that just applying the sum and the difference. So right here what we did was we just applied the sum. It was actually a difference, but we applied the sum difference law right here. Just saying, oh, we had a difference, so we can break this up into a difference. And then I notice that I've got a constant multiple right here. So this constant multiple can come out, and I can say, well, this is the limit of f of x as x approaches 1 minus 7 times the limit of g of x as x approaches 1. So right there, I'm applying the constant multiple law. Now, only for these first couple are we going to justify each of these, but we got to get used to using these laws and understanding that it's mathematically valid to apply the laws in this way. So I'll write it out for the first couple, each of the steps that I'm using, and then we'll start to combine the steps and bring these together. So now I'm to the point where I could actually look at the graphs and say, well, what is the limit of f of x as x approaches 1? So as x approaches 1, I come up to the graph. Here's x equals 1. I got to think about it from both directions. Notice that on the graph, the function from both directions is approaching 2. So this value is 2. So this is equal to 2. Minus 7 times, now I have to go to the g of x graph and do the same thing. So what is the limit of g of x as x approaches 1? Well, as x approaches 1, I got to come from both directions on the x-axis to 1 and see what's happening to the function. So what is happening to the function as x approaches 1 right there? And from both sides, we are approaching the value 1. So that's going to be 7 times 1. We're subtracting 7 times 1. And so this value right here becomes 2 minus 7, or negative 5. So the answer for this is equal to negative 5. Okay, showing each of the steps. Now I'm going to go ahead and I'm actually going to write the next one. Let's call this 1. Let's call this 2. I'm going to go ahead and write, well, I think we can squeeze 2 in down there. I didn't leave myself a ton of space here. So the limit of the product of f of x times g of x as x approaches 4. Well, the product rule says that we can actually look at this as the limit of f of x times the limit of g of x as x approaches 4 on each of those limits. And we could put this in. Why don't we put this in brackets here to really separate it? Okay. So that is using the product law right there. So there is the product law. So using the product law, we could say, well, what is the limit of f of x as x approaches 4? And again, I'm going to go ahead and erase what we had earlier up here on the graphs, because now we're looking actually as x is approaching a different value. So as x is approaching 4, so focusing in on 4 right here, as x is approaching 4, coming from both directions of 4, what is happening to the function? Well, the function is approaching, taking a look up here, the function is approaching this value on the y-axis. This function's value is 2. So this is going to be equal to 2. Get that in black. 2 times, well, what's happening? Go to the other graph. Go to g of x. What's happening as x is approaching 4 on the function g of x? Well, here's the function g of x. So as the x's are approaching 4 from the right and from the left, they are approaching the output, the function value of 3. So this is 2 times 3, which of course is a result of 6. So this answer here would be 6. Okay. All right, we are kind of squeezing it in here, but we're getting it in there. Let's do the next one. See if I can get it up on the graph here. So let's call this number 3. All right, so now we're doing a quotient, and the quotient rule, the quotient law, says that we can look at this quotient, the limit, as the quotient of the limits. We can look at the limit of the quotient is equal to the quotient of the limits. That's kind of a tongue twister, but that is what we're saying here with that law. So this is saying that we can look at the limit of f of x as x approaches 0 over the limit of g of x as x approaches 0. And so let's separate these a little bit. Let me pause this and I'm going to separate these a little bit. There we go. Okay, so that's what it says. Now, we do have to be a little bit careful. I'm going to scroll back up to, it's actually 2 pages back. I'm going to scroll back up to that quotient law just so we can have it on the same screen right here. Notice that in the quotient law, it is fine to do what we just did, right? We split it up as long as the limit of g of x does not equal 0. Now, of course, if g of x, the limit of g of x as x approaches a is actually equal to 0, then we have an issue with division by 0, right? This is the reason this law is here, right? You know, the stipulation is here is because of division by 0, right? Division by 0 is always an issue, right? So we have to be careful of division by 0. Okay, so that's why that notation is there. I want to mention that because when we come back to this example that we're looking at right here, as we approach 0, let's take a look at what's happening. I'm going to erase what we did on that last one. We were going to 4 on that last one. This time we're going to 0. So as we approach 0, so let's look first at the f of x function. As x is approaching 0, so of course here is 0. So as we come in towards 0 on the x-axis, what is happening to the function? So the function from the left and from the right are approaching this value right here, this value of 3 on the y-axis, an output value of 3. So the numerator here is going to be 3. And as we go to g of x, the limit as x approaches 0, of g of x, so when we head over to g of x, notice that we actually only have one side here, and so just to make this simple, I should have drawn that down a little bit. Let's make it look like that. There we go, there's g of x. So coming from the left and from the right, notice that right here, the function is actually approaching 0. And I'm going to put that in red because division by 0 is a problem. Okay, so division by 0 is actually a problem. And so what we would have to say right here is that this does not exist. And we are applying that quotient law right here, but we don't meet the stipulation. Now, we could take this a little bit further and we could consider infinite behavior. So we could definitely consider infinite behavior here. And if we wanted to do that, let's take this over just a little bit further so I have a little more space to work with. If we want to consider infinite behavior, we need to consider the two sides. So we need to consider the limit as x approaches 0 from the left of f of x over g of x. And we need to consider the limit as x approaches 0 from the right of f of x over g of x. Now, using the limit laws, we know that we can look at the limit of the top and we can look at the limit of the bottom. We already know that the limit of the top in both cases is 3. Okay, from both directions, the limit of f of x was approaching 3. So in both cases, from both the left and the right, so coming back over here to our f of x, we can see that the limit is approaching 3 from both sides, the left and the right of 0 as x approaches 0. Now let's look at what happens to g of x. So as we approach g of x from the, we're doing the left first. So from the left, notice what's happening right here on the graph. So as we approach, as the x values get closer and closer and closer to 0 from the left. We're thinking of something, plugging in something there like negative 0.001. We're getting closer and closer and closer to 0, but coming from the left, so we're negative. What's happening here is we're actually approaching 0 in a negative way. We're getting very small. Another way to write that is to say 3 divided by a very small negative number. Going off the screen here. Okay. We have the mathematical way to write that, and so this is the preferred way to write that. But just so we intuitively remember what that means, 0 from the left is a very small negative number. So if we're taking a positive 3 and we're dividing by a negative very, very small number, what is actually going to happen right here is this is going to approach negative infinity. I say approach, but what is a better way to say that actually is it is decreasing without bound. Okay, how about on the other side? What if we're coming from 0 from the right? So let's go back to the graph right there, and let's look at what's happening from the right side. So coming from the right side as the x's march in, that's what my tiny dots are on this graph, as the x's march into 0 from the right, what is happening to the graph? Well, the graph itself is approaching 0, but it's approaching 0 in a positive way, that those values there are positive. It's getting very small, but they are positive. So how do we express that? Well, we express that by writing 0 from the right, very small positive numbers. So again, just verbally, what am I saying right there? That this is 3 divided by a very, very small positive, and this on this side, positive numbers. And that, of course, as those numbers get smaller and smaller and smaller, is going to approach a positive infinity or increase without bound. Right? And again, the preferable way, we want to write it this way, but we can say it verbally. We can write it out as I just wrote there. Okay, so we could consider the infinite behavior right there, but I want to make a note here with that quotient law. As we're applying that quotient law, we got that doesn't exist because we saw that 0. That meant that we needed to do something else. That's going to mean check out what's happening there. This is more interesting maybe than the previous two where we were able to come up, use our laws and just work our way through quickly to get to a value for the limit. But here we actually had something interesting that was happening. And so we do, anytime we have this does not exist, we want to get in and we want to consider more what's happening. And in this particular case, the negative infinity does not equal positive infinity, or left does not equal right, right? We also have that justification going on. So there, let's get it all on the screen here, hopefully, so that we can see that whole problem there. Start to see the next one. Okay. All right. Okay, I'm going to go ahead and write number 4 and 5 over here where we're going to have a little more space to do these. So let's take, we have one more here we want to do. Let's take the limit as x approaches 2 of the product x cubed times f of x. Okay, so let's apply one more, let's do one more limit here. Using these same graphs, so I am going to erase what we've got going on there so we can clean up the graph and start another example problem here. Maybe we'll just do one more. We'll skip 5. Okay, so let's do this number 4. So if we're looking at this and we want to take the limit of x cubed times f of x, well, applying the limit laws, I can start by applying that product. So I'll apply the product law first, and applying the product law tells me that I can take the limit of x cubed as x approaches 2, and I can multiply by the limit of f of x as x is approaching 2. Okay. Well, we also have a power law that says that, so now let's write the power law. The power law says that this is the same as the limit of x as x approaches 2 quantity cubed times, and we'll apply it, we'll find this limit in just a second, the limit of f of x as x approaches 2. Okay. And then we actually have that linear limit law that says that the limit of x as x approaches 2 is simply going to be 2. So that linear limit law says that this is just going to be 2 cubed. Okay, linear limit law says that's just 2 cubed. And then we can actually take this other limit, and this other limit we have to actually do graphically because the function over here is given f of x, and we have to say, okay, as we approach 2, so coming from both directions to 2, what is happening to the function? And the function is approaching this value here of 3. So the function is approaching 3. So this is going to be 8 times 3, and this value is 24 using all of our limit laws. Okay. So on that one, I'll zoom in on that one. So that number 4, and we did have to use the graph. So on this one, we used the graph. Use f of x graph. Okay,